Hello everyone, I'm Nitin Reddy from Easy. My, my topic is the Prism efficient processing for the Internet of Things. Abstract. A new networked approach to signal processing efficient for both design and time real computation. It's proposed to match the requirements of the IoT. The Prism is a novel fire filter which is used fully recursive. The computational cost per sample is low and independent of the filter window length. The design cost is sample is low and independent for the filter window length. The design cost is low, also low. Any device capable of running a prism based signal processing scheme may also adapt it to match changing requirements. Various signal processing tasks can be implemented using networks of prisms. They were providing a useful tool set for a wide range of sensing the monitoring applications, including the Internet of Things. Introduction. The IoT and Industry 4.0 propose substantial increase in the deployment of sensors for collecting, processing, and communicating measurement data in real time. In diverse working environments, the challenges in realizing this ambition are considerable problems associated with complete cyber physical system CPS have implications for the design and operation of networked sensors. As systems became more interconnected and diverse, architects are less able to anticipate and design interactions among components, leaving such issues to be dealt with at runtime. Soon systems will become too massive and complex for even the most skilled system integrators to install, configure, optimize, maintain, and merge. Description of the prism. The prism is a dual layered signal processing object consisting of six networked integration blocks. Each block accepts an input time series and generates a corresponding output time series at the same rate. Each new input value is multiplied by the latest value of a modulating function with frequency HMH. The resulting product value is stored in the integration block along with all previous product values over the last 1 millisecond. The integral of this product values is calculated and this result gives the corresponding output value for the block for the current time step. This entire calculation is performed in each block for every new input value. The characteristics frequency M together with the sampling rate Fs and the harmonic number H fully determine the prism properties. Given the desired values of these parameters, the only design effort required to instantiate the corresponding prism is to calculate the linearly spaced sine and cosine values of the modulation functions. Hence, in principle, any device capable of running a prism can also design one. The mathematics of a prism permits recursive calculations within each integration block. The newest product value is computed and included in the updated integral values while the oldest product value is removed. Hence, only one multiply and accumulate operation is required to an integration block for each new input, so that the overall computational burden is low and fixed, irrespective of the number of samples in the data window of each integral. Application example. Prism signal processing is being used in a new Corliss mass flow meter prototype, providing a substantial increase in the measurement update rate and opening up new application areas. The Coriolis measurement principle is that the vibration of an oscillating flow tube transducer is monitored using two sensors, each producing nominally sinusoidal data. The mass flow rate is a function of the phase difference between the two sensor signals. In current commercial devices, flow update rates are typically no faster than 10 to 100 Hz. A previous ultra-fast prototype generated updated updates at 1.5 kilohertz. The new Prism-based prototype has been developed using a commercial flow tube coupled to a dual ARM core-based transmitter compute engine. This is capable of generating flow measurement updates at 48 kHz, and it's being used to monitor laboratory engine fuel injection, a previously unimaginable application. Plus, pulses of diesel fuel are injected through the meter at an equivalent engine speed of 1800 rpm and at 500 bar pressure. The mechanically noisy test environment excites additional mode of vibration of the flow tube, contaminating the sensor signals with the unwanted frequency components. Using precision signal processing, the Coreless meter provides an example of the substantial increase in measurement update rate achievable using Prism signal processing. But this same technique could benefit a wide range of other sensing and monitoring applications. It is particularly suited to signals with one or more discrete frequency components, where the frequency and or amplitude properties may vary with time, such as the measuring of resonance sensors or the monitoring of electromechanical systems. Potential applications may be found in a wide range of Internet of Things and indeed conventional fields such as industrial automation, transportation, healthcare, electrical power condition, and environmental monitoring and the smart home. With the figure which showing phase difference with or without notch filtering. Prism based Coriolis metering of diesel fuel injection pulses. And the Prism applied to the Internet of Things. The IoT presents significant challenges to a design and implementation of industrial sensors as discussed in the introduction. Prism signal processing addresses a number of these challenges, offering various advantages over well established FIR techniques, a recursive calculation enabling low computational burden, design simplicity, and a variety of filtering and attacking techniques. Prism technology can thus provide effective use of unavailable computational power and simple signal processing design for new sensors, thus reducing the burden on available design expertise. It offers a network style adaptability. Any field device capable of running prisms can also design them so that new signal processing scheme can be created as choosy as requested to require within device or a sensor network. This also affords a more open approach to algorithmic development. The sensor can be viewed as a local processor of relatively high bandwidth transducer data, where the exact data analysis required can be decided in real time and are in the application context rather than permanently fixed by the sensor designers in advance. Finally, the Prism offers an effective means of data compression by downsampling to preserve communication bandwidth. The correlations meter provides one example of a substantial increase in measurement update rate achievable using Prism signal processing. But the same technique could benefit a wide range of other sensing and monitoring applications. It is particularly suited to signals with one or more discrete frequency components where the frequency amplitude properties may vary with time, such as measuring of resonance sensors or the monitoring and electromechanical systems. Potential applications may be found in a wide range of IoT fields such as industrial automation, transportation, healthcare, electrical power conditions, and environment monitoring and the smart home. Thank you.